Okay, this is the third recording for the recent trends of smart materials course. This is lecture 3. Uh, we will start with the material that move. Okay, so before we start, let me show you this video first. So this is about the strength of materials in the nanoworld. This is a TED talk by Julia Good. I'm advising you to watch this by yourself. Dollars a gallon, 5 gallon. So this is to show you how the nanoscale is really important, especially uh, to produce new material that can provide a new property as well as the new strength of the material. So I will just skipping this all. Okay, please watch this first. Okay, this is the introduction for how to create ultra light and strong, and it is a fracture tolerant materials. So it will be combining the nanomaterial, the architectural design, and then the material itself. So by definition, okay, when we talk about the material that move, this topic is about the shape memory materials. We can say that it is kinetic materials, the terms. Okay. So the terms shape memory materials is the smart materials that have the capacity to remember, okay, a certain shape. Okay, so they can program or they can train to remember that shape, that certain shape. Okay, and how to trigger that shape change is by stimuli, usually temperature change, but it can be other than that. Okay, and then the important thing here, the shape memory material is not same. Okay, it's not equal. A material that has capacity to return to its former shape when the applied force is removed. So if you applied some forces to some plastic or maybe some steel or maybe metals, uh, when you apply force, you will see that the force making the materials bend or elastically bend. When you remove the force, the materials can revert back to the original shape, and that is not shape memory. Okay, that is elastic deformation. Okay, elastic deformation, that's difference. Okay, so the next is classifications. Okay, we have alloy, polymer, ceramics, and gel here. Okay, I think there's actually more, but I will restrict our classification on these four. So first is material based classification. So let's go for shape memory alloy. So usually in most of the alloy, the shape recovery or shape memory property is exhibited because of this martensitic transformation. So I will show you the video first. So what is martensitic transformation? So if you see, this is the grain boundary. Okay, this is the grain. So this is you see this structure like a needle shape here, like a needle, long shape here, and that is the martensite. Okay, that's martensite. So martensite happening because of the phase change inside the atomic structure. So and what happened in the macro scale, okay, let me show you these two videos. Okay, so this is the macro scale. So here's the effect taking place. So you can change the shape because of the temperature, and it will be went back to the original shape. Okay, So uh, the shape memory alloy, okay, it can be, it can have recovery property because of the temperature or maybe stress or maybe magnetic field, and this uh, deformation is because of this Martensite transformations. Okay, so I will explain later in another lecture what is Martensite transformations. Okay, so let me go back here and go for polymers. So polymers, uh, in shape memory polymers, we we are focusing on the cross-linking net points, okay, because it is the molecular switches. Okay, so imagine you can switch off and switch on, so between two states. Okay, and the stimuli can be light, heat, or a chemical agent. And inside these polymers we have also elastomers. Okay, elastomer is basically, it can endure, or has the ability to have a lot of elastic deformation. Okay, and also in elastomers there are magnetoroidal liquid crystalline elastomers, etc. There's some examples. Okay, so this is some video. I'm suggesting you watch this video. So I will show you the just the slide glimpse. Okay, so this is
This
the
face
polymers.
is made of a rubbery liquid crystal elastomer that responds
This is
to heat.
elastomers. Okay,
When
rubbery
warmed to about
elastomers.
80 degrees Celsius,
So
the material
it
loses its shape and
lose its
relaxes into a
shape
flat
because
sheet.
of the
When
heat,
cooled, the material pops
and
back into
then
shape.
it will back
To
to
make this shapeshifter,
original
chemists
shape
at Rice University had
when
to
you
strike a
cool down the
balance between the
temperature.
stiffness
Okay,
and flexibility of
so
each
that
form.
is,
Liquid crystal elastomers are made of liquid crystal.
and then I think this is like this is the, yeah, the same, I think the same similar materials. Okay, so you can change the shape like this. Okay, you can stretch it to a temporary shape, and you can stay for a long time. But when you heat, okay, heat the material, and this is the temperature in our body, just using our human body temperature, we can return these polymers to their original shape. Okay, I think that's enough. Let's go back to uh, these slides and go for the ceramics. So in ceramics, actually, uh, the ability for ceramics to be shape memory ceramics, it is almost impossible, because ceramics is crystalline has crystalline structures, and it is inherently brittle materials. Okay, so even small strains like 2%, it can cause a cracking. Okay, only a few cycles of transformation it can be, or it can cause cracking. But in uh, in research, some research, they found uh, they can make the ceramics, or they can alter the property of ceramics, and making it having the memory effect, okay, shape memory effect. So this is the zirconia. uh, you apply stress to that zirconia impact, okay, and then after a while it will release the heat, okay, and it will revert back to the original shape. I think this is important for like a shock absorber in car, or in any materials that have a chance or possibility to be to to get impacted for like impact or heavy weight here. That is ceramics, and then the fourth is the gels. Okay, so this is called the hydrogel, like this one. Okay, so hydrogel is uh, it's like a jelly. Okay, so if you put in the water, uh, it will have property like a water. When you put in the dry or no water, it will be like a gel. Okay, and there are smart gel where they can change the uh, volume because of some stimuli. And maybe uh, I will give you this one. Okay, the definition of a hydrogel. So hydrogel become water like this, having properties like water. It can absorb and retain a huge amount of water. You can watch this by yourself. Okay, and the examples for hydrogel, the easy one is the contact lens. Okay, and this is the what we call uh, the hydrogels for wound dressing. So they can trap water. Yeah. So you can use that for wound dressing, soft robotics. You can put some electronic circuit inside, and you can have many benefits from it. So that's the hydrogel. So this is the based on materials, and the second one is based on the stimuli. So we have heat, magnetic field, electric field, light, pH. Okay. So heat, we call this a thermoresponsive Shapememory material. And remember, the idea is heat is also causing the materials to be expanded, but the expansion, okay, the thermal expansion is not a Shapememory phenomenon, but it is a reversible shape change effect. Okay, so it's not the same thing. This is the examples. I'm suggesting to you to watch this by yourself. This is just a design, and what this design is, it will changing its shape because of heat. Okay, like this one, it can be like a dress. So basically it's like a textile, like a fabric, so you can put into the building. It will have like a layer here. It will close and open, depends on the temperature, or depends on day and night. Okay, so that's that. And the other,
Imagine a rubber band that stays. Someone has made one.
so this is the polymer
A research team at the
that can
chain
change its
molecule
shape.
consisting of
I think this is the
rubber
same
band,
as
which
the
snaps over
video
warms to around human
from
body heat
the
temperatures, it returns to its
previous
original shape. It can
slides.
also lift
Yeah, the
1,000
same
times
video.
its own
So the same
mass, meaning
materials,
this
the
polymer
same
can
property.
do work.
Okay,
Imagine stretching out.
so that's the thermoresponsive material. And the other property, or the other stimuli, it's magnetic field. Okay, we have the electroactive materials, the electrolytic fluids. We have the electric field, we have electroactive materials, we have the polymers. Okay, so you can change the form because of the response, okay, to the electric field. uh, this is also used as the artificial muscles, okay, because the response is similar to the muscle tissue. uh, yeah, we are using these polymers used for muscles because it has the lower density and higher resilience, and and you can design the polymers to be like fiber strands in muscles. Electric field also, we have the piezoelectric. Okay, so you can generate the electricity because of the displacement. Okay. So this is the examples how piezoelectric can help our our electricity. uh, mm, I think the video is already not available, but uh, you can check this tree. This is the same brand, the Pavegen. Okay, let me show you here. Yeah, you can click this one, or you can search on YouTube the Pavegen. So the idea is, you have the tiles, and when you move on the top of the tiles, the the piezoelectric materials inside the tiles change the strain into electricity. So that's the idea. And then light, uh, it's called the photoresponsive shape memory materials. So the materials will changing the shape because of the light. Okay, UV light and other part of light, it can be designed. Okay. And the pH, also for some hydrogels, mostly pH sensitive, so you can control the property of straight hydrogel by control the pH. Okay, usually for medical applications. So there's the kinetic materials too, and then this is the self-assembly smart materials. This is the 4D printing. Okay, so what it does is, you can program the materials to be able to remember some shape, and then it can self-assembly. Okay, so we have one dimensional, two dimensional, three dimensional, and now it's four dimension. So four dimension means we have another constraint, which is time. Okay, so during the period of time, we can have materials like this to be uh, to be able to self-assembly itself. Okay, so it will by itself self-assembly to some shape or some structure. Okay. So this is the future that maybe we will see, okay, in the next future. So you can self-assembly this part, so just shaking it and making the bulk ball like this one. So yeah, I think this is not only common smart materials. This is already advanced, okay, because it's not only the material, but it is also the design and the program inside that's already been complex and advanced. Yeah, that's the idea. The self-assembly, the 3D printing. Okay, so that's the the last video for this whole lectures, and this is the last sections. So I hope you get the idea for the kinetic materials or material that move. So basically what we have talked here from the material based classification and stimuli based classification is that is all about the basic, okay, the common smart materials that we already develop or available in the market. But what this video show us is how we can improve from that, okay, how we can combining all the technology, all the materials that we have, so we can make another uh, 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 another device or product that have all those functions, okay. So for example in this, for the printing, uh, because 3D printing, you have on you focus on building the 3D structure. The 4D, you focus on building the structure and dynamically have uh, 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 another set of functions. For example, during some period of time, the materials, it can self-assemble. So you print the materials, and the material itself will move out and self-assembly itself by itself. So you are making maybe some device. So you print part by parts, and over a period of time, these parts will come together and combine. So that's 4D printing for you. So it will reduce the time, okay, it will effectively reduce the time and also the manpower, okay. So you have part and you have the assembly, okay. So that's the idea that uh, we can learn and probably harvest in the future if you interested in smart materials. So that's the whole lecture for material that move for lecture 3, okay. We will continue these topics one more time in the lecture 4. So I hope you get the idea of this recording, and if you want to learn more, okay, uh, please watch the video. And I think the video before, you need to look for the I mean the piezoelectric, okay, the piezoelectric here, this video, okay. Please watch in YouTube, look for pave gen or electricity from your tiles, okay, because I think this video is already several years ago, and they want to change some aspect in there, so they close the or delete the video, but you can look for, okay, to get some idea. Yeah, so back to here. So yeah, that's all for this recording. Yeah, I hope you enjoyed the recording. See you on the next recording. Bye bye.